Hello, everyone. Welcome to Building Evolving AI Agents via Dynamic Memory Representations using Temporal Knowledge Graphs by Michael Banf.
Thank you so much. Welcome to the session. My name is Michael Banf. I'm the Chief AI Scientist at Parallel. And I would like to, what I brought today is kind of like a challenge that we at Parallel are frequently having, and actually I think which goes through the community, and that is that of reliable and adaptable memory architectures. So basically what we're seeing is this emergence of ever more powerful language models and AI models, and also more improvements in tooling and tooling interfaces. And it feels like a little bit we're lacking behind on the dynamic memory side because, right, we were dealing with truncated context windows with volatility memory and often quite almost no or just a huge lack of persistent understanding of user intentions and changes in environments and changes in user behavior. And to that end, it's very interesting. We need these adaptive memory architectures, and it's interesting because we actually have all the tools or toys, depending on how you want to look at it. We all have that available, right? We have very powerful graph database systems like Neo4j that serve as a foundation for memory systems. We have language models that can help us with extracting information. And also we have very sophisticated methods from geometrical and more recently topological deep learning that can act on graphs and can really help us to build these memory architectures, but still we have a way to go. And to that extent, I would like to briefly highlight and showcase some of the key principles and design principles for dynamic memory representations as foundations for evolving and immersive agentic AI systems that we at Parallel have integrate in our work and are circling around the community, and is basically food for thought for further development. And let's just dive right in. And I already mentioned graphs. So first of all, obviously the selection of a suitable memory architecture to hold context and context history, for us, that is actually graphs. Graphs by nature have a very transparent, that is human readable knowledge representation form. And in particular, they are sort of, as they are schemaless, they're inherently adaptable to changes and also for retrieval tasks. And they offer this efficient hybrid retrieval between semantic similarity and adjacency-based graph traversal elements. And this, they lend themselves to an intuitive path-based reasoning, right? Everything that makes them really, really suitable for really interesting setups for agentic AI systems. And as I mentioned, they're by nature suitable for geometric and topological deep learning aspects that we can integrate into our retrieval tasks. And the second principle after selecting a suitable memory architecture is that guidance, to really spend effort on like building a guidance design for the LLM-based information extraction as we're constructing the graph, as we're constructing our memory structure. And in particular, what stands out is the capability of using these structured output formats when we're creating our nodes and ontologies, building custom designed entities, and also designing multi-level semantics. So basically going from raw data over various types of ontologies, over clusters, or as I mentioned, integrate these methods from geometric and topological deep learning, building potentially hyper edges of that represent certain types of information into the knowledge graph, and making use of all the plethora of methods that we can make use of here. And it's basically use case dependent granularity, but that's kind of like the second thing, the second principle that we're dealing with. And on top of these, basically using those two as a foundation, we have this modeling of the temporal aspect. And that is actually the way, potentially the way forward in terms of like building these evolving AI agentic system, modeling temporal state changes with respect to information in a knowledge graph, with respect to ontologies, and also with user intentions and user interactions. And in particular, two things might stand out. The one is this key idea of like replacing the deletion of statements, replacing the deletion of facts and elements with kind of like a temporal invalidation, because that basically gives us that possibility of tracking the history of the evolution of our data, right? And really being able to use that between potential like facts that we've been learning, tracking this history of the evolution of our data. And the second one being the interactions, to model the interactions with a data structure by an agent or a user as entities within the same data structure. So in a sense, to be able to also track the state changes of, for example, intentions by user and the environments, in a sense that lends itself towards some sort of personalization, but also you can think of use cases like several sessions of a coding agent and basically learning for an upcoming session of what has worked in the past, what the user has been gone through, which step he has validated, which he has invalidated, and basically being able to provide that as context and use the graph memory as the data structure. And I would like to highlight, because the last part is maybe the most fascinating, most interesting one, I would love to highlight the modeling of temporal state changes, information ontology, and user intention by giving a quick illustration. Because the main question, and this is actually maybe the key takeaway from the session, is like the question of how can we and how should we model time in knowledge graphs. One way to model time, and it's been proposed in the Graphiti library, for example, is this idea of a bitemporal time model. So basically what we have here in short is sort of like a world, let's call it a world validity time interval and a system validity time interval. So basically the one tracks when a certain fact has been true or was true in the real world from when to when. And the second one, the system validity, tracks when a certain fact has been believed by our system, by the knowledge graph in a sense. And basically this kind of like timing model is very straightforward, been implemented as properties of nodes and edges using timestamps. And we're gonna later see this in a little example. And we can ask already very interesting questions and already build in a very straightforward way, kind of like a trace of a fact being validated or then might have become obsolete and so on and so forth. Or we can trace this history of a certain fact. And as I mentioned, to give a quick example here, we fabricated sort of like two scientific studies describing the effects of a certain inhibitor on blood glucose levels. And here we have one study from 2015, some fictitious study where we basically designed some fictitious drug, SGLT-I flow sign, that basically is described in its key findings. We're following here a little bit of the formatting of the Graphiti library, which we used to build this example, where basically the key finding is that it reduces blood glucose levels. And then we built this second study, which was basically came out a few years later, then 2019. And here we have the same drug. And in a sense, the key finding is that it turned out that it not only didn't have any effect on blood glucose levels, but also it showed that the first study had been performed poorly in terms of statistics. And so therefore the results have been wrong. And now what we do is basically we construct our little knowledge graph here. So basically we take the initials, the first study, and run it through our pipeline of entity extraction and ontology derivation and build an initial version of the knowledge graph. And as you can see here on the right, as I mentioned before, we can very nicely use custom entity definitions here, for example, based on the Pydantic library, very convenient in order to really make sure that the nodes are in the way that we want them to be. And following on the first study, we then update our knowledge graph with the second study, and then basically derive at our little knowledge graph here. So what you can see immediately is the different colored nodes representing the different entity types, which are described by our Pydantic models. The violet ones, the purple ones, are the original raw input studies. And here, this is displayed. Here, so you see the original raw data is stored, and then basically we have entities being extracted. In particular, what's of interest is the drug and also the blood glucose node. And we can also see we have here the valid and created at. So basically these kind of timestamps, they basically have the system and the world time being tracked for those nodes. And what's interesting is that after we run both studies in a subsequent manner, in order to update our knowledge graph, the summary for those nodes has also been updated. So originally this drug, as it was created as a node in the first study, and now been updated in terms of its summary. So the more recent finding of the 2019 study have been integrated. So that is one very interesting thing, where we basically within the node track the history of this fact. And that basically goes also for the corresponding blood glucose node. But more interestingly, in terms of visualizing this invalidation paradigm, this bitemporal model is, as we look into the relationship here, in particular the relationship that was built between the drug and the blood glucose level in the first study as a reduces relationship, and had a valid date. And here the valid date is corresponding to when the release date of that first study, so 2015. And so basically, after we integrate the second study, we see that there has been an invalidated date, right? And that goes to the release of the second study. And therefore, we sort of like simulated an invalidation of this fact after 4 years. And you can also see at the top the description of the system time, right? Since we ran these two studies and brought this into the knowledge graph within an interval of 2 seconds. Basically, the information expired after 2 seconds within system time, right? Okay, so that is kind of like an illustration of this bitemporal model, and we can ask different types of questions, and we can really nicely track the validity of this information and the history of that information. And we can go, as I mentioned, we can go one step further, and this is also something, a food for thought, is, okay, next to the data and next to the modeling of the changes, temporal changes in the data, what about the temporal changes of user behavior, the temporal changes of the interaction? And here what we did in our little toy example, we sort of like connected some little chatbot, sort of like connecting the user to that knowledge graph, and the user could log in as some fictitious clinician here, basically using the synonym fictitious clinician Sarah Chan. And as she logs in, we represent her as a user node. She has her own kind of like an initial history and specialty. And so therefore, she's already connected with some of the elements within our graph. And this actually allows, in a sense, for basically tracking her personal history. And then what we do is, as she interacts with a knowledge graph, here in a very simplistic, very straightforward way, and it's questionable whether we want to do it in production settings like that. But basically the idea being, we treat these medical consultations that she has with the graph, we model those as entity within the graph, right? So again, here very straightforward, we're basically integrating as content for each of those nodes the output of the chatbot at a certain stage, right? And I wouldn't recommend it to do in real life scenarios like that, but this is the food for thought in terms of like, okay, cool, we modify a knowledge graph as we're interacting with it, and we're tracing our own history, and also we can make cross connections with potentially like other users, right? And so there's a lot of food for thought, as I mentioned, and with that I want to wrap it up. Is actually the more interesting part, is the open question in general: how should time be represented in knowledge graphs, right? Because just to give you an example, the bitemporal model struggles if you have recurring events or if you have facts which are valid across multiple but non-contiguous intervals, right? So you basically run into bottlenecks, into problems with this straightforward bitemporal model, even though it's a cool idea in general. And therefore the question might be like, how should time be represented if we want to integrate that temporal dimension? Should it be just node edge properties, or should time be modeled as a more profound entity in a graph, right? So just food for thought again, time trees is one idea that floats around in terms of like being a structure, hierarchical organization of time as individual entities, and then linking nodes and edges which represent data and data interactions to specific time points. And it basically allows for a different view of time and also for different representation of temporal aspects in the knowledge graph, and allows for the address for asking different questions, but also might need different types of querying, right? And that for us, the parallel is actually as a driving aspect, driving question. And yeah, so I would love to leave you with this kind of question, and thank you so much for your attention.